Okay, so we are going towards non-blocking. We're taking our time. We first looked at all the system concepts, like interrupts and so forth, and we looked at, and we went there from I/O. Then we've seen how IPC can be cast as an I/O problem, a more complicated I/O problem where we needed the accept operation, the connect operation, we needed even byte buffers. And now let's get into blocking issues. Okay. So here's what we have with the blocking semantics. Okay, and these are the semantics in Java, and I assume these are the semantics in Python, because these were the semantics in Unix. Okay. And the question is, and already these blocking semantics are encouraging concurrency. Okay, if you have to send a bunch of bytes or a byte buffer, you block until at least one byte could be written into the byte buffer, into the system buffer. Okay, you don't wait for all the bytes to be written. So that's increasing concurrency. And similarly, when you read, you wait for at least one byte. Okay, or rather, you wait for you unblock when you get at least one byte. Okay, so the assumption here is that we want non-blocking. Non-blocking would mean that I don't wait at all. So if I can't write even a single byte, I still unblock. Okay. Similarly, if I got nothing to read, I still don't block. Okay. So the block operations, so the read and write operations don't block. So what used to block doesn't block any longer. Okay. And the motivation is that I don't want to block. I'm a busy person. I can do other things, so I don't want to block. Okay, that's sort of the intuition. So let's talk of some example that would need such concurrency. Some example where you don't want to block. So that's good. A UI has to go and process user interface operations. Excellent. And the UI should not. Maybe the UI thread is doing some kind of writing, sending some data across. So it shouldn't have to wait for the system buffer. And if it's doing reading, should the UI thread ever be reading? Well, if it's non-blocking, it could be reading. Okay. So what about your mail servers that you guys who did 431? Did it? How did you guys do it, by the way? I'm just curious. The mail server, you guys didn't create threads, from what I remember, right?
You just did console. You had to do every individual thing with the SMTP protocol. So just the headers that it expected in the message report. So that's kind of exactly what they were. You just like type one, and if the server said like, okay, now I'm expecting like a message to come across after you've specified the sender and like the contents of the message. I forget exactly what the format was, but it was basically like console I/O. You weren't as much interfacing with the sockets. It was like pretty simple socket coding and more focused on like maintaining states of the
Yeah, but still, you coded you didn't use any libraries, right?
It was just sockets.
You used sockets, okay.
But I don't think any other.
So you had accept calls, you had accepts,
Yes. Yeah.
right? When you didn't accept, you got new sockets in response to that. You could have multiple clients talking to a server.
No, we just did one-to-one server client.
I was wondering how you guys got away with not knowing this stuff for that reason. Yeah. Okay. So let's complicate your matter. What if your server was a true server talking to multiple clients? Yeah.
It could lost waiting for, it could be in the process of processing a message from one client and then ignore a message from the other.
So the question then for it is that it's got multiple clients. It needs to go and look at all the client channels to see if any data, any messages are there. If it picks up client 2 to read from, it has to do that in some sequence. If you're not using threads, you have only one thread to read. It's got n channels to read. It's got to pick some order. And let's say it picks up some client M. And the next message doesn't come from M, it comes from N. It's waiting for a message from M. Right? So now, using sockets, how would you solve the problem in Java? Just you can't go to non-blocking semantics. So or Python. Both. How would you solve the problem? If you have blocking semantics in the API, you would solve the problem by have multiple threads. Have a single thread per client. Each thread will block on its socket. Okay, now, by the way, the fact that each thread can block independently is a very big deal. Because in the bad old days, when a thread blocked, the whole process used to block. And that was the intuitive thing. If the threads are built in some user level code, for instance, to make them efficient, the operating system doesn't even know there's a thread going on there. That's a user level code. So it would just block the whole app process. So it's an extremely big deal that in Java, each thread could block independently on a system, on an I/O operation. Okay? And when Java was created, it decided that it was going to favor high-level programming rather than messy, low-level programming. And non-blocking means messiness. Okay? And so Java said, I know that non-blocking exists in this world. Not Java said, Gosling said. And I'm just going to give you threads. And I'm going to give you a very nice interface to threads and just create a separate thread for each of these. Okay? So I'll not take the mail example. I'll take our grader example, which will become real soon, I hope. And you have multiple clients. You have multiple grader processes talking to a dispatching server. And this dispatching server needs to know what to block on. Okay? And it could do what we just talked about right now. Have a separate thread for each student and have a separate thread for each grader. Grader meaning the grader process. Okay? And that was Java's solution initially. And what's wrong with the solution? If I'm a MOOC server, I have, number of threads. You could get a lot of threads. Okay? So NIO has been designed to create scalable servers. That's the key. When you guys go for your job interviews, say, I know how to do scalable servers. How? I know NIO. And if they know NIO, they'll get impressed. If they don't know NIO, impress them and tell them what it's all about. Okay, so just with assignment 1, you've gone far beyond what people can do with distributed programming. Okay, well, you haven't quite seen the underneath of NIO, but you will. Okay, especially with the midterm. By the midterm, you guys will know that very well too. Okay, so that's the key. Separate reading thread for each student in grader channel, but threads are expensive compared to method calls for scalable servers. Okay, so threads are cheap compared to processes. Okay, because they all share a single address space, but compared to procedure calls, they're expensive. Okay, questions so far? So what we want to do is the following. We'll want to create a single. What I'm saying is create one student thread, one grader thread. Why not combine both student and grader into one thread also? No, so we are going to get away from blocking. Okay, with blocking I can't do it. So what I'm saying is, ideally I want to do this, But blocking is,
They're sending like different messages.
they're doing different things. That's why I liked your UI example, I didn't like your UI example. I'm saying, why is the UI thread doing communication? It should be putting things into a bounded buffer and getting them to a bounded buffer. It's from separation of concerns point of view, it's not, but you might just, lots of people do it. So,
Web programming a lot of the time, but don't like UI blocking, and you might be doing something.
so web programming in the browser,
Yeah.
in the browser you have only one thread, apparently. I have tried not to, I shouldn't say I tried, but I just haven't looked very much into the web browsers because they just they constrain you. And so I believe you don't have multiple threads in browser. Okay, so you're kind of stuck with that. And that's a good thing. And that's why you want non-blocking. Right? So, but the main point is that, you want the threads to be doing logical pieces of work. Okay? And you would have both of these threads be different runnables, different kinds of runnables. Whereas when you had multiple student threads and multiple grader threads, all of the student threads would have been using the same runnable, okay? Because they're doing the same thing, they're just multiple instances. And you're saying we want different operations here, okay? So when you do it this way, the question becomes which of the various client ports should a client thread block on, which of the various grader ports should a grader thread block from, okay? And that is the problem. So the answer is don't block. Okay? And the question becomes, how do you then change this API that I gave you for blocking to non-blocking? And let's try to look at these changes in two stages. Let's first go and say, hey, we'll assume that polling is okay. Okay? And see how far we can get with that. And see how that changes our structure, and then we'll start looking at polling, okay, at removing polling. So assuming polling is okay, what is sort of the minimal changes you can make to this API to have non-blocking semantics? So my read right now, the way I've described to you, it reads until I get at least 1 byte. And then it tells you how many bytes I got. Write will block until at least 1 byte is written to the buffer, and then tells you how many bytes were written. So the what's the easiest way to sort of change this API? Yeah.
If there's not space to write, or if there's nothing to read, keep going and do something else, and then have that come back and get that again.
So what you're saying, so how does my read change, for example? Does my read semantics change at all?
Yeah, like you wouldn't, instead of blocking, you would just continue.
So what does read do then? So I said read this into this byte buffer. There is not. So what happens? What does read do if there's nothing available?
It does nothing.
Returns, and returns what value?
It would either return like null or return exception
Or just return 0?
or yeah.
Okay, it's already got an int there. It just returns 0. And when you do a write, normally it returns how many bytes were written, and it used to block till at least 1 was written, and now what does it do? So the post condition is changed. That the post condition earlier was that n is greater than or equal to 1. Now its return value is greater than or equal to 0. That's it. That's the minimum. I don't know if it's minimal, because minimal normally implies some kind of proof, but that's a very small change you can make to have a non-blocking API. Okay. So that's what we'll do first, and we'll just see how our code structure changes now that we have this API. So the API is easy to change. Okay, it just goes and you're just checking, can I read what is available right now? If it's 5 bytes, give me 5 bytes. If it's 3 bytes, give me 3 bytes. Whatever is buffered, give me that, and give me 0 if nothing is buffered. And write says, whatever space you have, use it to write my stuff, and tell me how much you wrote. And if it's 0, that's fine too. Okay. So immediate return and return values indicate success. Okay, but the values returned will tell you how much, whether there was success or not, how much was written out. Okay. So my connect, and I want non-blocking for all of these operations. Okay. So what does a non-blocking connect mean?
Just continue doing whatever you need to do as the client while waiting for that response.
So you don't block, you just send the message across to the server saying I want to connect, and you unblock. Okay. Except yeah. Sorry? No. What does accept mean? I did accept. What does accept? Accept used to block until what time? Until a client connect message was received?
So just send it and then whenever.
Then hang on. Connect sends.
Sorry, yes. Call accept and then keep doing whatever you're doing. And then whenever a connect is attempted by a client, it's just accepted automatically.
It's accepted automatically. That's one semantics. And I like that semantics. But how do you get the return value? Accept used to return back a socket channel, a socket.
Return if there was a connection or not.
Sorry?
Like you said, return 0 if no connection at that time, no accepted it.
So if there is a pending connect message, return back a channel. Otherwise, return null. Right? So these non-blocking semantics become very unintuitive. Okay. And write we already see. Return true if connection already is established already. So you can call connect multiple times, possibly. Okay.
So what does happen when it returns null? Does it then automatically accept the next connection, or?
Does it what? When you're talking it meaning what? Accept?
Yeah, sorry.
Return channel if connect message pending, otherwise return null. So the caller will go and say, oh, I got nothing null, I'll try again.
Okay, so it'll just send another accept.
It'll call another accept.
Oh, another accept, sorry.
Okay? So it'll call another accept. So you just keep calling in a loop.
Okay.
You know how you do web programming. You wait 3 seconds, do another call. And yeah,
Is that polling?
that's polling.
Okay.
Okay, sleep, if you put a sleep there also, it's still polling. Okay, and return number of bytes, 0 to length. Okay, read number of bytes received. Okay, again, it can be 0 or more. So that's how we've changed our semantics. Yeah.
No.
You fine?
Yeah. No, I like half rates my 100%.
So like why would this not blocking accept the authentication at all? Especially if you're just sitting there and
So, if you're sitting in a loop, you're waiting, right?
yeah.
No. So the idea is this. You do a. So let's talk of the mail server now. Suppose I want only one mail thread. How did you code with the blocking thing? You had to wait for client 1 and then client 2, then client 3, and if client 1 doesn't have a message, don't do anything. What are you doing now? In the loop,
Checking each time.
each client. Checking client 1, 2, 3, 4, 5, waiting 3 seconds, trying 1, 2, 3, 4, 5, till you get the message. Right? So with one thread, you'll be able to do all this. The server is scalable. It doesn't matter how many clients you put. It doesn't use more memory resources. Sure, the response time has got a little worse. Okay, the 3 seconds you waited, nothing was done. If a message came in that period, it wasn't serviced. Plus the CPU was used. The CPU is being used every 3 seconds. But this is a scalable server. It's going to be busy. You know, somebody or the other is going to be around to ask for a service. So maybe it's not so bad. Okay. The main point is we'll get rid of polling also. I want to go gradually to the solution that doesn't require polling. Okay. So I'm not saying the solution is good. Okay. but it's got some advantage. At least I can handle multiple clients with one thread. I couldn't handle multiple clients with one thread before. Okay. And what you could do is, you could do blocking. Okay. Because that you could block for. It's not targeting a particular client. Okay. The connect you could do blocking. The writes you could do blocking, and the reads you could do non-blocking. If a system let you mix all of these things, you could pick and choose which operations you want to do blocking and non-blocking. Okay. But we are just talking about how to go non-blocking on every aspect. Okay. Now in Java NIO, there is a method called configure blocking, true or false, and you guys might have seen that I set it to false. And I thought that I can just take the same program and change it, and it'll just block or not block. But when I went and configured it to blocking, I got all kinds of exceptions. So it's not so flexible as you might want it to be. And I don't think you can go and say I want connect to be blocking and read to be not blocking. In principle, I don't see why you can't do that. In practice, right now. So NIO is very new. It's kind of buggy. It's not understood well, but it's used. It's used in scalable servers. So I don't know if it's buggy or not, but according to the tutorial, it's not thread safe, at least right now. So it's evolving, I think, still. Okay, but it would be nice if I could just go and say configure blocking or not blocking, and it would just work. Okay. So I think if a program has been written to block, you can change it to non-blocking, but not vice versa. Okay. And that kind of makes sense because non-blocking uses more abstractions. So those abstractions don't make sense in the blocking case. So I think that's the reason why I got these problems. Okay. So now let's go and see how to create a single read thread for students, how to create a single read thread for graders, and we actually already saw this solution when I was talking of the main. Okay, so let's go and see what a method read from students might look like, and this is just flowchart. It's all at high level, not very precise. So you get to let's assume that we have a list of all students. Okay, so you go to the next student. There's a list that you're going through, and from that student you figure out what channel they have. Okay, so you go to the channel and you go and read from that, and you give it the student's buffer. Okay, so you'll have to keep each student's buffer separate. Sometimes you're getting data from this particular student's channel. Sometimes you're getting data from another student's channel, and you're going to use different read buffers for them. So you go and say channel.read s.buffer. Okay. And now, what do you do with the return value? So no, you have to look at the return value. What kind of return value could you get? Okay, so you can decide somehow magically whether you read as much as you were expecting. If you read as much as you were expecting, what should you do? Go on and so just imagine this grader. Grader got the student assignment the full assignment the grader was expecting. The student process got the full assignment, and now what will it do? Write to the grader. Okay. And if it didn't get completely the whole message, what should it do next? Loop to what point? Which read? The second step? Do you want to loop to that student, or maybe
you want to keep going to the next student?
You want to be more flexible?
Yeah.
Who knows, that guy's machine may have crashed in between, right? So you go to the next student. So this is a multi-channel loop. Even when you guys were doing sockets with blocking sockets, you had to have a loop. You didn't have a loop, but you should have had a loop that said, how many bytes did I read? And you would read from the same channel again. Because you're assuming blocking semantics, you're just considering a particular channel. But this is a multi-channel thing, that you are now reading from multiple channels, and that's the beauty here. that you're not blocked on a particular process. So service student read, and then go to the next student. And the service student read would go and buffer things with the grader. Okay? So that would enqueue write request for grader. Okay? And the grader thread, it's very similar. And when the grader gets a grade back from the grader, when the dispatcher gets a grade back from the grader, what should it do?
Queue it up to be sent to corresponding user.
So, to the student. So it's going sending the result back to the student. Okay? So enqueue write request for the student. Okay. And the write request, write buffer and full write, you're done. And if it's not a full write, where do we go next? We again try to be more flexible. Okay. Okay. And then we'll just, now that the write is over, we'll dequeue the write request. We're assuming that the writes are getting queued up somewhere. And once it's over, we just dequeue it. Okay, and now as long as we have position and limits in our code, we know that we'll write from where you left off last time. So the byte buffer is taking care of that, which is really nice. Okay. Accept requests, we know the pattern, we accept. If it's null, we go back and try again. And if it's not null, we go and do whatever we do with the new channel. We go and maybe put it in some hash table, keep it in some list so that we can multicast things. Okay. Okay, and then go back to accepting more. Yeah.
How do you go to the next request for accept? It doesn't accept a connection request from any client? Or are you trying to connect to a specific client when you call it?
So that's a good point. I might have multiple. So supposing I have multiple server socket channels. Okay. So I'm saying that we went and added these socket channels to some list that you're servicing. And I'm never dequeuing a service request here. So assuming there's only one socket channel, I'm just going from there and accepting it again and again on it. So it's a circular buffer. Imagine it's a circular buffer. And circular buffer meaning it circles around. It's not really it's logically a circular buffer, not physically a circular buffer. Logically that you just circle it. So there's a queue into which you only add things, you never delete things. You could delete things if you got, just underneath something else might be dequeuing things. So that's what I'm saying, and that's how the implementation in my system goes, that there's only one thread for all channels. But you could imagine having a separate thread for each server socket channel, in which case there'd be only one request essentially. Okay? So that's why in the write case, I dequeued the write. With accept, I'm not dequeuing anything. With the read also, I didn't dequeue anything. I just assumed that, a request to read from that channel was added, and it goes again and again and processes that. So it's a funny kind of queue. Okay, it's really a list, a set that's mostly immutable, but in principle it could be changed dynamically. Yeah, I didn't emphasize that point. Okay. And I think what you would do, though, logically speaking, is have different accept loops for different server socket channels. Because what you do when I say add C to appropriate read list, that's very specific to a particular port, and you'll probably have different
multiple socket channels if you're listening on multiple ports.
Yeah, like this, our server here. Our server here is listening to the grader on the grader port and the student port.
Gotcha.
Right? Okay, other questions?
I have one for the multi-channel write loop. So it is not full write, so it just goes to the next request, but it's not to queue that write request. So then when you loop back and you keep writing to that one.
Yes, if you could not finish the write, you don't dequeue it. You dequeue it only after you finish the write. That's what my logic showed. Okay. Okay. Connect loop. Seems pretty trivial, right? Next request, connected equals, you figure out whether it's connected or not. If it's not connected, try to connect again till you are told that the connection succeeded. Okay? And then the connect request you will dequeue. Okay? Because it's unlike the accept, you don't, where we try again. Once you connected, you connected. So this doesn't work. With accept it worked, with connect it doesn't work. In the case of accept, whether you accept it or not, you went and redid the accept, right? When the accept succeeded, you went and did some extra action, but you redid the accept each time. With connect, it doesn't work. Yeah, I know. I want you guys to answer.
Is it just like the same object? Is it just like a...
Side effects. Side effects. This is going back to Niels. He kept saying accept will send a message. And I kept saying, no, accept is a call. Connect sends a message. Now you see why this doesn't work?
You're never listening to the response.
Sorry?
You're not listening to the response.
So when I do, suppose, so when does connected become true? You get the response. And each time you do a connect, what happens?
It just continues going.
No, what is the semantics of connect? The first time you call connect, what happens? The client calls connect. What happens?
Send a message to the server.
Sorry?
Send a message to the server.
Okay, second time? Sends a message again. Okay? So, that's our problem. We don't want connect to send messages each time. I mean, just send one message. So connect is this funny operation. Is it a function? Is it a procedure? It's both. Right? It's like your it's like read line. Is read line a function or a procedure? It returns back a value. It's a function, but it changes what it's going to read from. It changes a pointer underneath, so it's a procedure. Okay, and those of you who, anybody by the way learned functional programming as their beginning course? None of you guys did. So my generation, that's what was considered the right way to learn. Okay, and people hated side effects because functional programming can't handle side effects, and then reads and writes became a tricky thing. One of my office mates went to IBM to sort of fix that problem, and 20 years later he was still trying to fix that problem. So it's just a tough problem. Okay. So anybody know what NIO does? I mean, what happens in this situation? Anybody look at the traces to see what's really happening underneath? So how would you solve this problem? You're a designer. You've got to change the API. We can't. We want non-blocking, but we.
Don't you have doesn't the class, there's a listener object?
No, that's my stuff. Look at NIO.
So not.
I'm just hiding all these things from you guys, okay? But the traces are showing you underneath what's going on. So if you are a designer of API, how would you change the API to fix this problem? I don't want blocking, yet I don't want to send a connect message again and again. Yeah.
I was gonna say maybe you get an object that is kind of like a promise or something. I don't know.
Yeah, right, absolutely.
And then the next time you call the next request, you get that object instead of the channel itself.
So you do, so the first thing, when you got the promise, you were calling connect, and that connect did what? Send a message. And then you got a promise, and that promise you poll again and again. And the promise doesn't send a message. Right?
Isn't that just blocking the promise?
No. Each time you ask the promise, it says, did I get back a message or not? So you're polling the promise. Okay? So, side effect of connect. Okay? Connect message send multiple times. Connect, now here's another term for you guys. It's not idempotent. Any of you guys math majors? Did you learn study the word idempotent in math? Sorry?
There's a propositional law related to it.
So just
I don't remember what it is.
good. Anybody remember what it meant? Good. Because this is totally different. Okay? So I'm not saying you keep two concepts in your head at one time. That is gone already. So put a new concept in here. So can you define what an idempotent operation might mean based on the fact that connect is not idempotent? Okay. So if I say add 2 and 2, how many times I call add, I get back the same result. Imagine an increment operation that returns back the value you incremented. I call increment 5 times, I get 5 different times. Okay, so in distributed systems, they talked about creating stateless servers. And stateless servers supported idempotent operations. Okay, so in other words, when you do a read, you don't go and just say read. You go and say read from this byte, read from this position. So if you invoke the read operation 10 times, you get back the same byte because you're always reading from the same position. Okay, so file servers they created as stateless file server, and they said, we don't want TCP/IP, we don't want all this overhead, we want UDP, and we just assume that most of the time messages will go across. So we'll create servers that are stateless, and we'll support and we are idempotent operations. Okay. So idempotent means that multiple invocations of idempotent operation. If an operation is idempotent, is equal to the single invocation of the same args. Okay, so if you say 2 and 2, add 2 and 2, it's always 2 and 2. If you say add 3 and 3, you get different values. But the same call, the same command object results in the same value each time. Okay. So we now have another method. It's not a promise. We just invoke this operation in the same channel. Okay, but it's a promise. Okay. So we have connect. We call it once. And now you go and enqueue a finish connect request. Okay, and we'll assume that there's a buffer available to send the connect message. Assume there's a dedicated buffer per connect channel that you don't have to go and block on it and do a loop to know whether the connect message went through or not and whether there was enough bytes or not. Okay, and DQ connect request, that's a loop there, and that's the loop I showed you earlier. We're not calling connect again and again, we're calling finish connect again and again on the channel object itself. Okay, because there's only one connect operation you can do on the channel, so I don't have to go and return back a separate object for each connect. There's only one connect that you would do, so I can just call finish connect on that connect object, and we do this. Okay. Questions? Okay. So we have, if you look at your logs, you'll see finish connect and connect. Okay, and so there are two different operations there. So finish connect is idempotent, connect is not idempotent. I've split these two operations. Connect is guaranteed to succeed because we'll assume there's a buffer there to write a message. Okay, and finish connect is the one that we poll again and again to see the return value. Okay. So my API has changed. I have both a connect and a finish connect operation. Okay, that's what the real API has. Okay. So what are we doing now? We've got one read thread for each port. That's our programming style. We have a separate write, accept, and connect thread. Okay, I'm assuming there's only one thread for all channels. Okay, which may, like I said, in the accept case, you might want a separate thread for each port. And if you can imagine the main thread, the main worker thread. Okay, this is my grader. This is not general. This is how I did my grader. Okay. So it goes and creates these requests, and that is processed by connect and accept threads. So the main thread, the main program comes up. If it's a client, it goes and says these are the ones I want to connect on. If it's a server, it says these are the server socket channels I want to accept. Okay. So connect and accept thread create channels processed by read threads. Okay, so if it's a client, the channel that's created by the connect thread is the one that's processed, and if it's a server, the channels created by the accept thread are the ones that are read. Okay, so I'm just trying to sort of complete the whole picture, and read threads create requests for write thread. Okay, which we saw. Okay, so that's our solution, and we are out of time. So we'll just carry on from here next time then. Okay. So we were doing looking at the server code, and we were looking at how it should be structured in terms of threads, given that our server will talk to multiple clients, possibly an unbounded number of clients. And we saw that when we had blocking semantics, then a server had to create a separate read thread for each client that might write to it. Okay, and the client might be a student client or a grader client, and so we had to have two kinds of threads. Okay, and that makes your server relatively easy to code. Okay, but it makes it non-scalable because we have just a lot of threads, and we can argue that threads reduce performance. Okay, so we went to non-blocking semantics, and we said, how can we get single read thread for? So we'll still have multiple threads, a separate thread for the grader clients, a separate thread for the student clients, but we'll have because they do different things. But we'll have only one student thread and one grader thread. We won't have n student threads if n is the number of students. Okay. So our code became more complicated than in the synchronous case, than in the blocking case. Now in the blocking case, you should be reading in a loop, okay, from even a single client, because we don't know how much you might read. You don't know how much you might read in one shot. And now you have to also sort of, you have to have two levels here, that after each, so your read statement now will tell you how much was read, and it could be 0 now. Okay, in the blocking case, you're guaranteed to read something, and probably everything when the read returns. Now you're guaranteed to read nothing. You're guaranteed nothing about the reads. So you have to, in a loop, assuming polling is okay, go back and try reading, and you're not necessarily trying to read from the same client you read last time. You're just trying to read from the next possible client. Okay, that means you have to keep state regarding how much you've read from each client. Okay, so the coding is messy. Now, those of you who've done operating systems, or even if you haven't, based on what I've told you already, can you argue that this is trying to mimic the job that the kernel does when it's doing thread switching? When it's doing thread switching, what does it do? It maintains some data structures, right? And what did we call those data structures? That data structure? Process control block. That's keeping track of what that process or thread is doing. Now I have to keep track of how much I've read from each client. I have to keep a separate buffer for each client, maintain a buffer for each client, and keep track of how much I've read in that buffer. Okay, hopefully the buffer keeps track of that because we're using the Java data byte buffer, but still I have to maintain a separate buffer in some table. So I'm doing context switching, right? And so this code is not very clean. Okay, this is like a manual context switch, and I want to sort of argue here that, on the one hand, I'm going to fewer threads to increase scalability, but I am going to messier code. And you should use threads when you can, and it doesn't spoil performance because otherwise you're doing manual thread switching. So threads are not just there to get concurrency. Threads are there to also make your code easier because the operating system is doing certain context switches that you don't have to do yourself then. Okay, so it's much cleaner to have multiple threads. Okay, so we are going to faster computation, but we are going to less clean. And typically it is, do you want efficiency or you want clean code? Efficiency, go to machine code, maybe assembly, maybe C. They're all similar to each other. You want modularity, you go to high-level languages. And they don't always oppose each other. The garbage collection in Java can actually make things much faster because you don't have memory leaks. And there was a parallel computing professor here who benchmarked, and he looked at the C++ implementation of a server and a Java implementation of a server, and he found the Java implementation was much faster. Okay, so it doesn't always conflict, but we have a problem of manual context switching which we have to solve. Okay, so we now have two loops which are reading from clients and from students and grader clients. We also have a loop for write. Okay, again, we are not just looping on a particular client, we are looping on multiple clients, so we're keeping write buffers for different clients. Okay, we had an accept loop, okay, where we don't just block on a particular accept, we block on accept on a particular socket channel. If you have more than one server socket channel, we block on all of them. We don't block at all, but we keep testing all of them. Okay, so and then this sort of pattern got destroyed by Connect, because this whole idea of repeatedly trying reads, writes, and so forth makes sense as long as the multiple reads and writes don't cause any problems. As long as but when they cause problems, then we have to make sure that we do, when they have side effects that cause problems, we have to make sure the side effect occurs only once. So Connect is different. Connect has an effect that when you invoke Connect, it sends a message to the server. You want that message to be sent only once, but you don't mind waiting for the connection multiple times. So we broke the Connect into two operations. The sort of initiate Connect, which is called Connect, which sends a message done only once, and the finish Connect, which is done multiple times to see whether the message arrived from the server or not. Okay, again, we're not blocking, but we're just waiting for the message to arrive. Okay, and that you can do multiple times till you get back a connection status true. Okay. So we looked at the notion of an idempotent operation. Idempotent operation is an operation that you can do multiple times without causing any problems. And distributed computing people have used that term, so have mathematicians, but that term means something else, and have used it to because it's important. You can create stateless servers that don't depend on any state, and so they can actually tolerate message losses. So you don't have to use TCP/IP. You can use UDP. Which works most of the time. Okay, and by the way, just to show you, just to sort of motivate that, so we way back I'd built an RPC system that worked for both UDP and RPC means remote procedure call and TCP, and whenever I had to give demos to funders, I would go and make it UDP because I knew it would be much faster, and I knew the messages won't be lost. And so even though, for reliability purposes, for the real users, we had TCP/IP on, we just, it just made a big difference in performance when there was UDP. Okay. And messages never got lost. We were working on a local area network anyway. Okay. So to summarize, now we don't have a read thread for each client. We have a read thread for each port. Remember, a port is for each service kind, for each port number. Okay. Remember, we have a port number for each service kind, and we can have multiple clients that use the same port number. Okay. We have a separate write thread, which can be generic. We have a accept thread and connect thread. Okay. In our grading example, at least, they could be they could be just one thread. Okay. So I'm just talking about not a general thread structure. Well, this is general too. It's got general aspects too. Okay. And in our grader example, the main thread creates requests processed by connect and accept threads. Okay. So the main thread in the server goes and enqueues an accept request. The main thread in a client enqueues a connect request. Okay. And the connect and accept threads create channels processed by the read threads. Okay. So they go and say, when the channel is created, then they go and tell the read thread, hey, start reading from this, or start from the corresponding thread for a channel. And read thread creates requests for the write threads. Okay. So the client read thread creates data for the grader write thread, which writes to the grader ports or channels, and the grader read thread enqueues data for the student. Okay, so this is, now we've got a nice, bunch of threads talking to each other, and you sort of see thread communication at work to make a whole program work. Okay, so we understand this. As long as we tolerate polling, as long as we tolerate all these context switches that are manually done, we've at least got a smaller number of threads than we had with the synchronous solution. Question? So let's see what the problems are. We still have multiple threads. It's not as event-waiting threads. We don't have just one thread. We don't have unbounded number of threads. Okay, but we do have, depending on the number of ports, certain number of threads. Okay, one for accept, one for connect, one for read, one for write, and then depending on how many ports there are, a bunch of read threads. Okay. Threads perform context switches, not very nice. We'd like to get rid of this problem. Okay. NIO will not get rid of this problem, but we will through the NIO manager. And the reading threads have code duplication. Okay. The reason I created two different reading threads was because I had to do something different for after the read in each case. In the case of the client, I had to send data to the grader instead of the grader. Sorry, in the case of the student, I had to send data to the grader and vice versa for the grader. So just the post-processing was different. Everything else was very similar. I'm going through a bunch of channels, trying to read as much as I can into buffers and converting these buffers into data suitable for the writing thread. Okay, so we had to get rid of the code duplication also. Threads need to poll. Okay, so that is the problem. So we need blocking. So here we're sort of going in between. When we had blocking, we had lots of threads, so not scalable. Now we have fewer threads, but we have to poll. If we're not going to poll, we need blocking, but we're in a cycle now. So how do we get rid of the cycle? You want to have the cake and eat it too. Few threads, no polling. Bounded threads, but no polling. And you guys know enough about NIO to attempt some answer to this question. Or you can try to use your imagination. So I don't want an unbounded number of threads. Ideally, I want one thread, but I'll deal with 3+ port threads. I don't want to poll, which means I need to block.
So you need some kind of signal.
You need something to?
You need a signal, something to
So you need blocking.
Yeah, you need blocking.
But when I had blocking, I was in trouble. So maybe I need some different kind of blocking. So how will my blocking change? When I had blocking previously, I said, okay, the read operation is blocking, the write operation is blocking, the accept operation is blocking, the connect operation is blocking. But then I didn't know which one to read from, which one to connect from if I have multiple options. So what's the key here? Yeah.
It's kind of like what we did with the bounded buffer. Some are blocking, some are not blocking, right? So we can.
Okay, so I can make some non-blocking, but then I need to pull in those cases. So I can try to have a hybrid solution where there's some blocking and not blocking. So I want to have the cake and eat it too. It's not that I want to have few cakes and eat few cakes. I want each cake to be, yeah.
Do we need some sort of selector thread that like dispatches the jobs to the other threads and blocks when it has nothing left, and just unblocks when it gets incoming pending requests?
So what you're saying is that it unblocks when it. So previously I would unblock when I'm blocking, I would block for either the read event or the write event or the accept event or the connect event. So now I should block for. So I would block for the read event on a particular channel, or the read event on another channel, or write event on another channel, and so forth. And what you're saying implies I should block for any event on any channel, or multiple events on multiple channels. That's the key. That's a selector idea. Okay, and it took a while for the solution to come out, and it took a while for the community to come up with the solution too. Okay, so from what I remember, Ada was the first language to have this idea. How many of you guys have heard of Ada, the language? You have, and the Ada language was, what do you know about Ada language?
So like, the programming languages course that we offer here?
Yeah, did you take that?
Well, I'm taking it, but at UNCC, my older brother went to UNCC. The way they structured that course is you were given a language and you had to make a project, and he was assigned with taking real-time ATC data and trying to create flight records in Ada. And he said it was like the most fun he's had in a course in a long time.
I love Ada, the language. And Ada, the language, is named after? And who is she? First computer programmer. And Countess of Lovelace. So why was she Countess? Any literary person here? Can you make a literary connection to her?
Did she write like the letters for someone?
Letters with someone?
She like was a scribe for someone.
She was a programmer. Scribe for somebody. Lord Byron. You guys know who Lord Byron was? Sorry? So she was his daughter. And so anyway, that's the countess part. Okay. So Ada had a notion of selection, and then that feature came into Unix also, and that's what you see in Java. Okay. So a blocking I/O operation waits for a particular event on a particular channel. Okay, but that leads to the problem of thread proliferation. So we're going to have blocking, but we should be able to block on multiple operations on multiple channels. That is the key. Okay. So that raises a whole bunch of other issues. Okay, so we had this problem that when we had the original blocking semantic, this is the questions we had to answer, and we had to create multiple threads. Now we'll say that our student thread will block on read and write events both, okay, on all student channels. Okay, so that's what the student thread will do. The grader thread will go and block on both read and write operations on all grader channels. Okay, so we'll still keep these two different threads right now. Okay, but we'll just we will combine the writing thread with the student thread, and the two writing threads, with both the parts of the writing threads with the student thread and grader thread, and so just not have any blocking. You just have no polling now. Okay, so that's the idea. Yeah. Questions? So what we could do is we could have a select operation that says block on all pending operation on all channels. Okay. Suppose I was to give you this particular operation. This is not what NIO gives you. What would be the problems with this? That's my select operation. Block on all pending operations on all channels. Yeah.
Maybe you only want to block for like a specific operation, and it'll just be broken up needlessly.
So, and in our example, I couldn't have a grader thread and a student thread doing different things because we want to do different things on unblocking. And I couldn't have two different sets of things happening. Okay, so if we did that, so I'm trying to see what I'm saying. Okay, so I should be able to select which channels it blocks on, okay, to solve that problem. So I'm sort of gently saying that, look, this is a problem, and we should be able to select which channels to block on. Okay, so now my select operation is getting a little more complicated. I can't just say select. I have to say select a bunch of channels. Okay. Now here's the question. So when I was doing a read operation, I said I want to do a read operation on this channel, and unblock me when that operation succeeds. So there was no mystery as to which operation got done on which channel. That was what I was waiting for. Now I'm waiting for multiple channels and multiple operations. So how do I get to know when I'm unblocked what actually occurred? Now, how would we, what do we need here? In the abstract, let's not get into the detail. When I unblock, I need to know what? Yeah.
Need some message saying what specifically is unblocked.
So the unblocking should have some return value that has nothing to do with return value of the operations you're blocking on, but tells you which operations are ready. Okay. So on unblocking, wait should know which channel operations are ready. Okay. So which operations on which channels are ready. Okay, so I need some kind of result value. Now, that's the basic idea here. What that API, what exact nature that API takes is a detail. Okay, but this is the basic idea that now you're unblocking on multiple events, and when you unblock, you get to know what events are. Okay. So here's sort of the API. We'll create now we see why the channel, the socket channels that we had, we were calling them selectable channels because they're selectable by a blocking operation. So they're selectable operations, and you can say whether you want to block or not. You can have an object called selector, okay, and you can register the selector with a channel. And I find this kind of counterintuitive. I'd rather have the channel register with the selector, but it goes this way around. But basically, you're creating a binding between a selector object and a channel. Okay, so your select operation will be invoked on a selector. Okay, that selector can be connected to multiple channels. Okay, that's what happens when you register a channel, a selector with a channel. Okay, so you can say something like, selectable channel dot register selector, and you get back some return object called a selection key. Okay, what's the selector got? How do you create a selector? You use a factory and say, give me a selector. Okay, so you don't instantiate the selector. You just go and use a factory. And what happens underneath is that this particular class that got instantiated, that has some reference to an operating system data structure that will actually do the weighting. So that's why you don't really instantiate it. You just get something from the operating system. Okay. And what can you do to it? You can select, and you're selecting for at least one new event, and there's a return value that tells you how many events got enabled. Okay, so if it's just one, it'll return you one. It'll be at least one. And we need some way to figure out when the select select returns, you need some way to know what operations got ready. So remember, when you registered an operation, it was like you got a selection key, and now you can go and figure out which of these keys is ready. Okay, so think of the selector as being a bunch of registrations. Each registration has got a key. It's like your number. When you go to some place, you want to wait for something, you give your name, or when you go to a restaurant and say, I want a table, you go and give your name, and when a bunch of tables get free, it goes and tells you which tables are free, right? So that's the basic thing. The table number or your ID is the key that you got, and then you get back selected keys. And what do you do with the set? So once you know which channels are ready, what do you want to do? So supposing you know that a particular channel is ready for read, what do you want to do with that? You want to read it, right? So you can go and say, okay, are you actually, so you can at that point go and say, are you acceptable? Are you connectable? Are you readable? Are you writable? And so you get back a key that's associated with the channel. To figure out which operation is ready, you can just go and ask it, which one is ready. So it's a way to go and meet the requirement that I told you earlier, that when select returns, when the blocking returns, you want to know which operations got enabled on which channels. Okay, the Unix had a mask that it returned. There was different ways to do it, and this is just the API, and it's just one way to do it. Okay, so we get to see the concrete syntax here, which you guys didn't quite see directly, but is being used underneath in my implementation. Okay. So here's a new problem. I've got this select call I'm making, okay, and I've decided that I'm going to have the following coding, that the student thread is going to wait for read and write operations to be, either the read or the write operations to be ready on the student channels. Okay, and that's hopefully going to stop me from blocking, from polling. Now, when is the read event going to be ready? Whenever new data arrive. How often will the write event be ready? Write operation be ready. So the write operation is ready when? What condition? What is the condition for the write operation to be ready?
You have to process a read first, so you're getting data from the client, then you do something with it, and then you're going to want to write it back to it later.
So that's the algorithm, that you will first read from some place and then write it back to some other place perhaps. So you read from one channel, write to another channel. The read operation on a channel is ready when there's some new data to write. The write operation on a channel is ready when the other end is able to read. Do you really contact the remote kernel?
There's something in the queue.
The write operation is ready when when there's something to write. Not quite. When there's an output interrupt given again?
When there's enough buffer.
When you have a buffer space to write. When you have buffer space to write. Hopefully the system is going well. You'll always have buffer space to write. Okay, it's only in the rare condition when there isn't buffer space that you wait. So my loop that's waiting for read or write to be ready will almost always not block. Unless your buffers get full, it will always be sort of just pulling away. Okay. So what do I need to do now? How do I change this? So I think I've got write operation will usually be ready. So I'm just continuously unblocking. So I registered my channel, all my client channels with the selector. Then I said unblock me whenever there is any operation ready on this. Whenever I get unblocked, I go and say, is it ready? Is it writable? Is it readable? If it's writable, I write the next piece of data. If it's readable, I get that piece of data. So that was my algorithm. It's not working very well because I'm just continuously ready. So at least the API I gave you is not serving that purpose. The basic algorithm we had in the beginning, the idea we had was served. So how do I change the API to accommodate this? And this is something you guys have seen in your traces and in the discussion of the assignment.
Doesn't it, after it processes, the call select again and then unblocks and adds write to its interest operation? Again?
Interest operations. We didn't have interest operations in the previous slide so far.
Well, yeah, but like under the covers, isn't that what it was doing? And then it would unblock again because then.
No, under the covers where? Under the covers of NIO manager or under the.
In your code.
My code.
Yeah.
I'm talking of NIO right now. We haven't come to that. So we need the notion of an interest operation. We need to not just register a channel with a selector. We need to register an operation and a channel together. Okay? So should wait for write readiness only when we have data to write. So we don't want to just continuously wait for write. Only when we have data to write do we wait for write, and once we have written the data, we stop waiting for write. So reading we might do continuously because we always want to read from the clients. But writing we wait for only when we have data to write, otherwise we don't wait. Yeah.
Because in your code, I see that you comment out one of the listener, which is called bounded buffer, it's empty. You commented out. Is that why?
No, that's a different thing.
That's different.
It's a different thing. I just changed my implementation so you didn't have to go and call that code.
Okay.
But we'll get to that. Yeah.
When you say when there's nothing left to write, you just stop waiting to write? What do you mean by stop waiting to write? Like, what are we doing instead?
So how are we waiting? We are waiting by saying select. We associate the select operation with a bunch of interested operations. Okay? So when we have written the data, we say, after the data have been written, we tell select, we're not interested in waiting for write any longer. We're only interested in waiting for read. So as long as we have pending writes, we wait for the write to occur. Otherwise, we don't wait for it.
So
And we wait for write by indicating the interest operations.
what do we gain by not waiting on write anymore? Just a couple
If we wait,
wasting as much time in each cycle or whatever?
no, but you didn't get what I said. Write operation will always be ready. My select will unblock. I'll go and say, is it writable? It says yes. I say, well, I have nothing to write. So I'll go back. Is it readable? No. So I'll go back and wait for it. So I'll continuously be unblocked. Don't you get that? Write is always ready. And I'm not interested in write. I've written my data. So I don't want to know that my write has occurred because I have no pending write. Read is what I want now. But when I have data to write, Then I go and say, okay, did the write finish? Is it ready? Do you have a buffer? He said, yes. Okay, I'll write it. Okay, did I write it completely? No. Okay, I'll wait again for write. Okay, did I write it completely? Yes. I'll go and change my interest stops. That's your interest stops. Okay, so that's the part that you guys had to worry a little bit about in your assignment. What is, especially for the accept and connects. Okay, and the fact that the write ops I did automatically in response to your writes. Okay, so I was doing that automatically. Okay, and as he's pointing out, that when all the writes were over, I went and changed the ops automatically for you, and I also changed it back to just having only read. Okay, so that is the part that you didn't have to worry about. Yeah, I commented on. Okay. So interest ops makes fine. That's what we talked about earlier, that we want to select which operations and which channels. The API that I showed you earlier just let you select channels. Now we want to select which operations. So we need equivalent of disabling and enabling of output interrupt processing. We had the same problem with output interrupts. After the outputs were done, we just disabled the outputs. We went and said, okay, don't bother to interrupt again. Our output has all been sent. We have nothing else to output. So we'll just disable interrupts till we have something new to output, in which case we'll enable output interrupts and get output interrupts again. Same idea is happening here also. So now my register takes not only the selector as an argument, but also the interest ops as an argument, which is a mask of which operations you want to wait on. Okay. So now it becomes selector, comma, selection key dot opread or opwrite or opread or opwrite. Okay, so there's a whole mask. Okay. Now here's a problem. My selector is blocked on just the read operation. Now I have some data to write. I wanted to block on either the read or write operation. So I want to change the interest ops dynamically. Okay, that's what happens here. You can tell this, you can invoke the operation interest ops on a selection key to go and change the set of operations dynamically. But my selector is blocked. It's not even there. I mean, it's just blocked on read. And how do I tell it to change the set of operations it's blocked on? Because it will go and look at the operations it's blocked on are the operations that were of interest when it executed the block.
You have to re-execute it.
You have to re-execute it. And how do you sort of re-execute it? Wake it up. Okay. So how to make block select use new interest ops or registration, and you guys might have seen in your traces. Okay. So after a new registration, whether it's a new channel that you registered or a new opry you registered, you want. Okay, so that's what's happening here. So there's a wake up operation, and that wake up operation is executed to wake it selector up. Okay, so in your logs you must have seen that. So you see it's getting quite complicated right now. Here you have a bunch of operations, but that's the joys of asynchronous programming. Okay, questions? Okay, now here's the interesting thing, or the not so interesting thing, depending on your viewpoint. So we have multiple threads going here. We have a selector thread, which is which blocks on, does a select, and we can have multiple selecting threads. We have other threads that are changing interest ops and changing the behavior of what the select does. the selector object and this key objects are shared objects between the selector thread and the other threads. Right? The selector object, the keys, they're all shared between multiple threads. Whenever you have data structures shared among multiple threads, you need to worry about thread safeness, whether that access causes problems or not, multiple. And according to the Rocks tutorial, the Unix implementation of selector and selection keys is not thread safe. Okay? So there's a little problem there that we have to deal with, and the solution. So thread that blocks on a select may not be the same as the one that registers or changes interest opts. Okay, so we have multiple threads dealing with data structures. Okay, so the actions may not be atomic; they may not be thread safe. Okay, concurrent programming is very tricky. People make lots of mistakes. In fact, there was an industrial person I asked, and I said, what kind of bugs do you get in your code? These are good programmers. He said the two kinds of bugs we get the most are thread issues, thread safeness, and UI issues. Okay? So dealing with UI input, those are the things that cause the biggest headaches. So, I don't know why they're not. I don't know whether this guy, the author of the Rocks tutorial, is correct or not. Okay. So ideally, we should have a single thread that does select, register, and change of interest op. We don't want multiple threads to be changing data structure. Okay. And another thread can call wake up for a blocked selector thread. That's okay. But the interest op should be changed by one thread, and so that so the tutorial recommends a single selector thread in an NIO application. So far I was saying we can have one thread for selecting all grader channels, another thread for selecting all student channels, and indeed the way Java is implemented is advertised, that should work. That probably does work. I'm not sure whether he's right or not. Okay, but just to be on the safe side, we want one thread for this reason. So we'll just change this into, and so there's a more fundamental reason to have that also, that we have a code duplication problem here. The student thread and the grader thread do the same thing, except on unblocking they do different things with the read data. Okay, so that to me is a more interesting problem. What the Rocks tutorial says is probably a transient problem, if it really was a problem. This is a more interesting problem that I want to combine these two threads into one. So software engineering hat, how do I make sure that I can just have one thread, yet have application specific processing of the events?
Register a different class for different events.
So register, and what kind of class would you call that? Command object, listener, what would you call it? So command is the answer that I provide. Why not just say, just register listener? Sorry?
You're listening for a specific event. It's not.
Yes. Okay.